So at the same time, I will bring us to the YouTube side because usually we have 5 to 10 people on the YouTube side.
Mm-hmm.
Okay, it's setting up, maybe takes a few seconds. Okay, now we are good.
Okay, so let's start. So hello, everyone. Welcome back to our CFSM seminar today. So it is our great pleasure to have Dr. Ryan Pearce to give us a talk on the power limits in small and fast biological and engineered system. So Ryan is an assistant professor in the Department of Mechanical and Aerospace Engineering and Computer Science and Engineering at the University at Buffalo, working at the intersection of micro-robotics, microsystems, and biological systems. Prior to joining UB, he was a postdoc research associate at Carnegie Mellon University. He received his PhD in 2018 from the University of Maryland and a master degree and a bachelor degree in 2013 from Northeastern University. His research interest focused on bringing micro robots towards autonomy through understanding both highly dynamic biological systems and resource constrained robotics. His work in micro robotics has been recognized with the Best Paper Award at the 2018 Solid State Sensor Actuators and Microsystems workshop, and Ryan has been highlighted on the 2020 Forbes 20 Under 20 Science list. That's so impressive. So with that, let's welcome Dr. Ryan Pearce to start his talk. And Ryan, so now you can control the screen now. So.
All right. Well, thank you. So thank you for the introduction. 2 small corrections. My surname is St. Pierre, and it's Forbes 30 Under 30. I wish I was under 20 in 2020, but you know, the time goes on. I'm really excited to share some of my work in thinking about these really small, fast systems in both biology and engineering. And this might be a little bit of a departure from a talk that is normally seen in these seminars, but largely on a day-to-day basis, I think about really how do we make engineered systems that rival their biological counterparts? And how do we use our tools as engineers to understand biology better? And so that really gives us this framework for design and control. And so really what I want to start talking about is, well, what are the components of power? So power in just a mechanical system is force times velocity. And if we break up force, it's mass times acceleration times velocity. And since we're really thinking about power limits, it's advantageous to think about power density, which is power over mass, which is then just the product of acceleration and velocity. So what I ultimately want to probe is, how do we get these high acceleration, high velocity movements, and what are they limited by in our engineered and our biological systems? And so what can we learn to design robots better, and what can we learn from biology in order to see how these high acceleration, high velocity movements are created? So we start with all the constraints, because what is life without a bunch of constraints? So any biological muscle, the force from a biological muscle scales with area. And so if you go to the gym, work out, make your muscles bigger, you are getting a bigger cross-sectional area, which means you produce more force, you are stronger. And that is, you know, ultimately the goal of going to the gym. But with our muscles, we have this attachment distance, and so we have a lever distance. And so the work that our muscles can do is then going to be force times distance, which gives us work, which gives us energy, which gives us joules. And we see that that actually scales with volume. And one of the consequences of that is that the energy density of our muscles, which is joules per kilogram, scale is scale invariant. So that means no matter how big or how small you are, the force that you can produce and the energy that your muscle can produce per kilogram is the same. And this has actually a lot of consequences when we start thinking about power. So this means that if we take all of our energy that our muscle can use and convert it into kinetic energy, so our idealized system, we have no losses, This means that we have that 1/2 mv squared is also going to be scale invariant in terms of mass. So we have 1/2 mv squared divided by m is just 1/2 v squared, which means that velocity, the velocity that comes out of our muscles, is scale invariant. So the structure of our muscles, and this makes sense from a physiological perspective, is all about the same for most mammalian muscles. And so we get the same velocities for our muscle fibers. And so we don't actually get any advantage from being bigger or smaller to get any increase in velocity. And this seems like a big problem, especially if we're thinking about how power is generated in these systems. And then because we're engineers, we also like to think about, well, how do other actuators perform? And so if we look in the literature, looking at how some of these other synthetic actuators, in this case, DC motors, we see that our torque provided, which is the same units as work, is also scaling with mass, which means that our DC motors, in the most ideal sense, are also limited in energy density. So our DC motors, no matter their size, is still going to give us about the same joules per kilogram. So we seem to have a problem so far. Even if we look at other really exciting MEMS systems, I really like microsystems and MEMS. I've always loved them. If we look at how other synthetic actuators, either electrostatic, electromagnetic, piezoelectric, we're seeing a similar trend. We're seeing that energy is scaling with volume, which means energy density is scale invariant, or we're actually seeing that energy density gets worse with some of these MEMS actuators. So we have huge problems now. We have that our synthetic actuators scale similar or worse to muscles, so we don't get extra velocity in our systems, which means that power is mass times acceleration, and we don't get any advantage of making our system smaller or bigger to play with velocity. So we have to start taking our inquiry and going into, well, how do we get high accelerations? And if we want to circumvent some of these limitations on power. So one of the things that we look at when we think about actuators is this other constraint, and it's a force velocity trade-off. This means that for no velocity, you get a super high force. This is your blocked force. And for your free velocity, you get no force. And so we can connect these 2 points with a straight line from blocked force to free velocity, and we get the straight line. If we integrate this curve, then we get the power over velocity, and we get the peak here at about 50% of the force, 50% of the velocity is where we find peak power in any of our actuators. In the biological world, this peak power per force kilogram is set, and it belongs to this quail. So this quail has the highest force density actuator we would ever know of, and it's about 400 watts per kilogram. And this is because this is muscle structure that's involved in flight. And so this gives us the upper bound of how our power in our actuators. So this gives us our upper bound of anything that we could ever see in biology for our upper bound. So anything above 400 watts per kilogram is breaking physics in some kind of way, or it's doing something interesting that we want to investigate. So this means that we have these 2 giant constraints when we think about actuators. We have no additional velocity with scale, and our force velocity trade-off limits power through limiting both velocity and acceleration. So to get these high power movements that we see in these high acceleration movements that we see in biology and engineering, we have to do something different. And that something different is using springs. So springs help us circumvent some of these constraints. And when we think about this, we usually think about direct actuation for our biological systems and our robotic systems. And what this means is that we have a muscle attached to either a limb and we can move it around, or we have a motor attached to a linkage and we move it around for our engineered system. But what we can do is bring in a latch and a spring. And instead of using our muscles to power the movement, now we're using springs. So we're going to take our muscles and we're going to stretch these rubber bands or shells, whatever you want the spring to be made out of. And we're going to stretch the spring or compress the spring, and we're going to latch it in place. And now we're storing a whole bunch of energy. And then once we release the latch, our movement is now powered by the recoil of the spring and not by the actuator itself. So we've now shifted what dynamics are making our parts move. So instead of being limited by the dynamics of the actuator, we're now considering the dynamics of the spring as our actuator to circumvent these power limitations in actuators. And this has really cool, in my opinion, really cool consequences for the types of movements that we see in biology. And so one thing that I like to show is, how high are these accelerations in these biological systems when we start powering our movements with springs? So this is a plot with acceleration, mostly in a log scale, on the vertical axis and mass on the horizontal axis. And we see these super high acceleration movements, up to 10 to the 8. This is for a cnidarian, and I'll tell you exactly what that is briefly. But we see cnidarians, fungi, we see nematodes, we see arthropods, we see plants, and we see vertebrates, all doing these super high acceleration movements. And, we all know that fungi and nematodes and arthropods and plants and engineered systems all use various motors, and they use various actuators. But every single movement here uses a type of spring to get that high acceleration. And so we see like accelerations that are, orders of magnitudes higher than gravity, powered by springs. So a cnidarian is actually a stinging cell of a jellyfish. And what it does is really cool. And so this is a high-speed video of the stinging cell of the jellyfish. It is an incredibly high acceleration movement, but that acceleration dies out very quickly. And it's just a very short distance. And so the whole purpose biologically of having this very high acceleration for a very, very small part for just a stinging cell of a jellyfish is actually just to circumvent the Reynolds number. So it's Reynolds number hopping. So it allows you to go from, single order of magnitude Reynolds numbers to 3 orders of magnitude Reynolds number. And it allows the jellyfish to pierce the boundary layer of its prey item. So if it was not able to generate these high accelerations, this stinging cell would never actually pierce the boundary layer of the fluid. And so it would never actually be able to sting its prey item. And so it needed to actually evolve these super high acceleration movements to circumvent the limits of fluids in order to get its next meal. And another interesting system that I look at are trapjaw ants. And so right here is a trapjaw ant, just the mandibles. And so trapjaw ants have these, about 1.5 millimeters long mandible. And what is really interesting about them is they power these and they fire them and they close their mandibles. And this is closed in less than 300 microseconds. So it's going from 0 to 90 degrees in less than 300 microseconds. And this is an incredibly high power movement, an incredibly high acceleration movement. And this is also used for hunting prey items. It's also used as escape maneuvers. And we even see the same principle in robotics. So this is a flea-inspired robot, and it uses SMA wire in order to trigger a spring. And this video is maybe about 10 years old at this point, but it's still one of the more impressive flea-inspired robots. And it's even doing a really great high bar jump. So this system of springs and latches is what allows us to do this, allows us to circumvent these limitations placed by actuators on power. And it allows us to get these super high acceleration movements across a diversity of systems. So across engineered systems, fungi, plants. And it allows us to really think about this in a new, exciting way, and allows us to ask questions as engineers about design, control, and ultimately performance. So there's, of course, caveats when you move to a spring. So moving from one system in biology, so moving from muscles to springs, does not come for free. And this is, of course, going to have some form of trade-off. So what our new system is looking like is now we have a muscle that's going to pull the spring, and we have a latch that is then going to be released, and the spring is going to power our movement. So we have actuators are now storing the energy in our spring. So one thing that arthropods do really well is arthropods have the advantage of having these force modified muscles. This is not something that's available in the mammalian toolbox of design, but this is something available in the arthropod toolbox of design. So they have these very, very slow muscles that are super high force, which allows them to store a lot of energy into a spring over a very long amount of time, which allows them to power their movements. So they do trade off this very fast response to having high energy. We also need to evolve some type of latch, or we need to design some type of latch as engineers. So if we just start pulling the spring without a latch, we just have our regular directly actuated system when we get no advantage of storing energy in a spring anymore. And then we also have to rely on latches to release the spring to power the movement. So we need all of these components into our system in order to get these super high power outputs. And I think there's also some really interesting caveats that come with this. So one thing that I always find really surprising, and whenever I teach this topic, my students always find it really surprising, is that springs don't actually increase jump velocity. So this is a bunch of data from a bunch of different jumping arthropods at 3 orders of magnitude in body mass, and you see almost no discernible trend of any sort of increase or decrease with respect to the log mass. Sure, there's about a peak around 10 to the minus 5 kilograms, but we're really only looking at 1 to 6 meters per second in jump velocity. And what is super interesting here is that means that a grasshopper like this jumps with the same takeoff velocity as a flea, even though they are different body masses. And so when we think about this in the context of scaling and in the context of having our systems, we know that the muscle's force scales with area, which means that force is equal to spring constant times distance, which is then scaling with area. So that means that our elastic energy, which is 1/2 kx squared, is then going to scale with a volume. And so our elastic energy density is also scale invariant. So the real big caveat here is that while springs give us higher acceleration, we don't necessarily get higher velocity. So the real crux of this is that we get to circumvent these power limitations, not by generating more velocity, but by using springs to help us generate very, very high accelerations. And we see this in particular because this cnidarian cell, it looks pretty slow, but it's just high velocity is just used, its high acceleration is used to pierce that boundary layer, but that boundary layer just really slows it down very quickly. And so all we're doing here is just generating a super high acceleration movement, and we don't really care about distance or velocity. So the other big caveat that we have once we move from a muscle actuated system to a spring actuated system is that the energy has to be loaded by an actuator into the spring. And as I alluded to before, arthropods usually use these force modified muscles, which makes them really slow. And so another system that I studied during my postdoc was snapping shrimp. And I think snapping shrimp are really cool because they snap their claw underwater. And they do this so fast that they generate this cavitation bubble, and a little bit of plasma is there. And if you are down in North and South Carolina and you go off the coast and you stick a hydrophone into the water, you can actually hear what sounds like Rice Krispies. And it's actually a bunch of snapping shrimp just snapping, and the collapse of the bubble is what you hear. But what I want to point out is that it takes a really long time to be fast. So the snapping shrimp itself takes about around 500 milliseconds to load its claw. So on the left, we have a video that's, although it's filmed at 50,000 frames per second, it's actually downsampled, but it takes about 500 microseconds to end up closing that claw. So it's about 3 orders of magnitude of time is needed to prepare for these super high acceleration events. So that's that other big trade-off that we have to consider, is that it takes a long time to be fast. So what we're ending up doing is we're trading sustained power that we can provide with an actuator for intermittent high power that we can provide with a spring. And just for context, one blink takes about 1/3 of a second. So in the amount of time of one blink, you're watching a snapping shrimp load its claw, but it would be about 1/1000th of a blink is the time that it takes for that snapping shrimp to strike. So you are trading you're trading off this time scale. And so you have to be okay with the fact that you can't have sustained high power. And then the third caveat, which is really exciting for us as roboticists and us as engineers, is that control has to be reimagined. So I mentioned that we need a latch in order to block the release of energy from a spring. And historically, latches have been thought as these binary abstractions or as switches. They're either blocking the release of the energy or they're out of the way and all of the energy can come out. But what we've discovered is that when we start to add some interesting dynamics and interesting features to latches, we can bring in this new dynamical regime, and we can allow this new set of dynamics to be where we can start injecting control into our synthetic systems. So, in our LAMSys systems or our latch-mediated spring-actuated systems, we generally go through these dynamical phases where we are latched and we loaded energy into our spring. And then once we start unlatching our system, we can then use the unlatching features to delay and modify how energy is coming out of the spring before we get to these spring-actuated movements and these ballistic movements that are responsible for these super high accelerations. And so this feature of unlatching allows us to think about latch delay, and it allows us to think about control in these systems in a new and exciting way that allows us to design for control and engineer control into our synthetic system. So one of the ways that we studied this was actually through a biological data set on Dracula ants. So Dracula ants are really interesting because they push their 2 mandible tips together and snap like we would snap with our fingers. So you can see them push the mandibles together. You see a pretty good deformation of the mandibles, and then they slide past each other and they snap. So these are also called snapjaw ants as opposed to trapjaw ants. And what's really interesting for us is that the ants themselves have major and minor workers in their colony, which allows us to look at 2 different sizes of ants. So we were able to take this data set that we've got from a colleague, and we were able to look at both the latch velocity, so how fast the latch mandible is being moved over these against the strike velocity. And what we're actually able to see is that for the minor ants, we see a insensitivity to how fast the latch is removed to how fast the strike is. And for the major ants, which are the bigger ones, we actually see a correlation of behavior between latch velocity and strike velocity, which means that there is some parameter tuning that can happen. And we can start to imagine control through this latch removal property. And this gives us, a new toolbox or a new feature to play with as engineers when we start designing these systems. And so this gives us that third caveat when we talk about moving to spring actuated systems, is that latch removal has to be considered as a methodology for control, which allows us to tailor how the energy is coming out of the spring. And we're actually able to show this in a synthetic system in a jumping robot. And so we have a DC motor attached to a gear system that removes a latch, and actuating that DC motor at different voltages has the advantage of removing the latch faster or slower, which will then tailor the jump height without actually tailoring the amount of energy stored in the system. So that means that we can actually tune the range of jump height without actually needing to either physically redesign our system to store more or less energy. And it allows us to think about using latches as a controls tool in these really, really small resource constrained systems. So it allows us to have this control after the fact, and it allows us to think about control in the design stage of these systems ourselves. And so we can see, we get almost another body height once we actuate it between 3 volts and 8 volts. And this is pretty exciting as we start to look toward making these small, fast systems autonomous. All right. And then the other way that I like to think about control is actually through geometry. And so I like to think about that this snapping shrimp on the left and this robot on the right actually operate with the same set of physics, and they operate with the same set of dynamics. And they look nothing alike. And I think that when people tell me that I do bio-inspired robots, I think this is always a good slide to show them that although I am using the same physical principles, my robots look nothing like the animals that we probe and we understand in order to build these robots. So the snapping shrimp and this robot, they both use a torque reversal system. So that means that they share the same latch, and so they share the same types of dynamics that allow for energy to come out of a spring. But the robot uses an electromagnet in order to actuate and load energy into the spring, and the snapping shrimp itself uses muscle. The snapping shrimp has apodeme, which is the arthropod equivalent of tendon, and the robot just uses a piece of polymer. But the latch being the same is what allows us to probe these questions about control and designing for control through geometry. And so what a torque reversal system is, very briefly, is that it's a system where in the snapping shrimp, we are loading a spring above a pivot point. And then as we trigger our system, we're rotating that spring down through a pivot point. And so as we're getting to the pivot point, the torque is decreasing. As we cross over the pivot point, the torque has now reversed sign. So in this system, it's going from counterclockwise to clockwise. And so the torque reverses as it unlatches. And so when it's in a counterclockwise system, it allows the spring energy to be stored, and that geometry acts like the latch. And once it rotates through the clockwise configuration, that's when the spring recoil is going to power the strike of the snapping shrimp. And so in simulation, this is what it looks like. We see this teal spring being loaded, and I do want to point out the time scale. So right now it's ticking away at single milliseconds. And so we get to where that spring energy is loaded, and then the spring rotated down. And now the simulation is ticking away at microseconds. And what we're going to eventually see is that we've crossed that threshold. Our torque has now reversed, and now our system is moving in the microsecond timescale, and it's moving under the recoil of the spring. And so this whole sequence of events in simulation only is about 400 milliseconds, just still incredibly. And I will point out that the majority of that time was spent just loading the spring. And so this allows us to take a model like this from our understanding of shrimp and think about how we can map inputs to outputs through a torque reversal system, which will eventually help us figure out how we can design in control into our systems. But this allowed us to do a lot of work thinking about snapping shrimp and how they get energy in and energy out and what affects that and what perturbs it. So snapping shrimp, they take a really long time to load the spring. So they take, over 300 milliseconds, and they take very much under 300 milliseconds to close their claw. It's about 300 microseconds. And so in this plot, you can see that, disparity of timescales where the loading duration, if we look at the claw rotation, it's not rotating because the spring is being loaded. It's a flat line for a very long time. And then once the onset of striking happens, it looks basically vertical. But when we took all of this data on snapping shrimp, so we had 8 different individuals, we took up to 13 strikes on a single snapping shrimp, what we found was that we didn't really see a correlation between the loading duration and the strike duration. And so the plot in the lower right-hand corner is the coefficient of variation, which is a statistical tool that helps us look at the relative dispersion of the variance to the mean. And so the coefficient of variation is defined as the standard deviation divided by the mean. And so a very, very low coefficient of variation means that there's almost no standard deviation. A very high coefficient of variation means that you have a very high standard deviation. And so what we can see is that all of the coefficient of variations for this strike, the purple circle, is really, really low, and it's almost seated towards 0. Whereas the triangles for the loading duration is pretty high or relatively higher, and generally above this 20% threshold, which is what biologists use to denote whether a movement is stereotyped or non-stereotyped. And so what we found was that there was really no correlation between inputs and outputs in our snapping shrimp. And that really begged the question about why. So in this investigation, our inputs are the energy loaded in, but we're black boxing that, or at least we're measuring the inputs just based upon the strike duration, the loading duration. And our strike duration is what we're going to measure for outputs. So this allows us to do a couple different things. It allows us to not have to do a bunch of digital image correlation and do high-speed video tracking of rotations. So we're just doing timescales. And it also allows us to not have to take derivatives of numerical data, because as soon as we start taking derivatives of numerical data, our error propagation blows up, orders of magnitude, especially in these systems. So what we can do is start to unpack these boxes for inputs and outputs, and we can look at the energy loaded into the spring and unlatching as our inputs to our model, and our outputs are the kinematics, but we're going to be using time. So we parameterized a model with 3 different input parameters. The first is energy loading duration. So how long does it take to load energy into the spring? The second is energy loading rate. So joules per time. So what is the slope of that line? And then the third is the unlatching rate. So how fast does that spring swing through to the pivot point to the torque reversal event? And what we're able to do is actually look at the model kinematics against our biological data, and we found it's a pretty decent fit. Like, it's an abstracted version of this model. We weren't intending to model the snapping shrimp exactly, but we're intending to model the behaviors. And so we saw that this is good enough for our approximation. It's good enough to make some of these insights, but it's never going to be the end-all be-all snapping shrimp model, but it's really good for getting us insights into how a torque reversal system works. So what we want to do is then perturb each one of these inputs, and see the effect on the output. So we did this systematically, and we first perturbed the energy loading duration. And we found that the longer that you put energy into the system, the faster your strike is. And this makes sense because you're putting more energy into the system overall because we are keeping the energy loading rate constant. The next thing that we perturbed was the energy loading rate. So just the slope of this line was perturbed, but where the line started and stopped for the energy was the same. So what we got out was about the same loading duration, but we got a spread in strike durations because we got more or less energy into each of our systems. And then the final thing that we perturbed was the unlatching rate. And so this, after all of the energy was loaded into the spring, how fast does that spring rotate through to the pivot point and trigger this torque reversal event? And so we saw, some correlation, some variation between those two. And when we then take all three of these and allow them to randomly vary without any covariance matrix modeled, what we were able to see is we saw a slight negative correlation in 100 simulations of a simulated snapping shrimp. But overall, if you take any 10 of these points, we kind of return the same amount of variation, the same trends that we saw with the snapping shrimp itself. And this allowed us to start asking some of these deeper questions about geometry. So now that we have this model and we have this way to stochastically perturb and stochastically view how the inputs and outputs are being mapped, we get to start asking how geometry affects inputs and outputs. And this starts to get back to that original question of how do we design control into our systems? So the way that we did this was we parameterized these two geometric parameters. So the first one is the dactyl starting angle. So how open or closed does your movement start at? And the second one is this torque reversal angle. So this torque reversal angle is just the angle that's created from taking a straight line from the pivot point to the spring insertion point, and then the angle from that to the horizontal is the torque reversal angle. So the spring itself has to rotate through this torque reversal angle in order to unlatch. And so we were able to look at this space and look at a average snapping shrimp case. And we were able to see that, of course, when you start your dactyl in a more closed position, the strike takes less time to complete. And that, intuitively makes sense. But the other thing that we found somewhat interesting was that as you make a steeper angle, so we make a steeper torque reversal angle, and we go across for the same opening, our strike duration also decreases. And this is because after your torque reversal event, you now have a different profile of torque acting on the claw itself. And this is where we can start to make some of these changes and start to think about how do we get the behavior out that we want. And what I actually found the most interesting is that we can then combine our inquiry from before using this stochastic parameterization with this geometry. So we can start to think about, well, how does geometry affect variation? And this is where we developed a somewhat novel metric of coefficient of variation ratio, where we looked at the coefficient of variation of striking over the coefficient of variation of loading. So we divided two coefficient of variations by each other. So it's still unitless. And what we found was that if we look at this over a set of stochastic simulations over this grid, we can see that we get this gradation of coefficient of variations from the crossover point to the away from that. So some really salient features of this graph is that anything in this white space is actually no longer a torque reversal system. So the geometry would prevent it from ever latching and ever unlatching. And so in this white space, all we have are directly actuated systems. And then this boundary is where we jump from a non-torque reversal system, so a non-spring actuated system, to a spring actuated system. And at this boundary, we find that we get the lowest coefficient of variation ratios, which means that both the same set of stochastic inputs produces a lower set of outputs, which means that the variation is attenuated the greatest, the closest you are to this boundary, which means that you can now use these points to say, I want a system that is highly insensitive to stochastic variation inputs. And so I should design my system along this boundary so that almost all the attenuation is nullified through the mechanical system, and that we can get almost the same output no matter what set of inputs we get. But we can also turn this on its head, and we can say, how do I design my system so that I have the most range of controllable outputs given a set of stochastic or non-stochastic inputs? And so that allows us to think about design for our synthetic systems. So stepping through this allows us to then take what we learned about a snapping shrimp and apply it to a robot that looks nothing like a snapping shrimp. So this really, really simple, just like 2-link robot, we can do a couple different really interesting things. And so we can actuate it with different voltages. And so different voltages gives us different takeoff velocities. The jump isn't super impressive in this video because this robot weighs 300 milligrams. And so the tether attached to the robot provides a substantial amount of force to it. But this also allows us to take some of these interesting consequences, and we can design the natural length of the spring, which now allows us to play around geometry. And in doing so, we see different behaviors of these two systems. So for a longer natural length of the spring, we are jumping quicker, but we're also jumping with less energy. And so this allows us to think about designing that behavior through both geometry and through springs, and allows us to have this controllable output in these really, really small systems. So if we look at the space over geometry, we can actually see that we can get these yellow bars where we have a correlation between the torque that we apply to our electromagnetic motor and our takeoff velocity that we get out. And then if we have these slightly orange, we also see a correlation along this design space. But we can keep moving on this geometric space, and then we can move to a system where we have almost no correlation between the torque we apply and the takeoff velocity. And so this allows us to take our understanding of torque reversal systems, and it allows us to start thinking about how can we move on these design spaces where we can get a system that is either correlated to what we put in, and the performance is correlated to what we put in, or not correlated. So for a small jumping robot system, this allows us to have a couple different consequences. So if we're a small jumping robot, we have a pretty limited battery and a pretty limited energy source. And if after every jump you are depleting some amount of your battery, you would want to design on this space where you're pretty insensitive to those inputs. And so you can get the same jump performance out more consistently, more repeatedly, despite the variation on your inputs. This also has the other consequence of saying, well, I have very limited control on board in some of these systems, but I want to have a tailored jump or a tunable jump. How should I design my robot so that I have the highest correlation between inputs and outputs, so that I can get the most out of my limited system. And so when we start thinking about these systems and start thinking about designing for control, we can look at, how geometry is affecting these performance measures, and how we can design for control or design for stereotypy in our small resource constrained systems. And I think that, these pretty short stories on spring-actuated movements have a couple really interesting consequences when we start to design robots and we start to probe biology. So the first one is that moving from directly actuated to spring-actuated movements can greatly increase power density, but of course it's coming with these limitations. And our spring dynamics are now what is dictating the dynamics of our systems, not the actuator dynamics. And it comes with these considerations that you have to be okay with when you move to a spring actuated system, that it takes a long time to be fast, which means that you are trading off sustained power for intermittent high power. And it requires you to think about how controlling the output of the spring is more indirect. So you can't control the actuator itself like we would in normal mechanical engineering approaches where we can actually feed into the actuator. We have to now think about how we are tailoring the energy coming out of the spring. And we can design our robots and design our systems for control, but we have to think about these holistic systems, and we have to think about springs and latches not just as features that we need to get high power output, but features that we can tailor to tailor the energy in and out of a system. So I think that in general, one of my biggest takeaways in working in this field is that understanding the foundational and fundamental physics of biology and probing these systems kind of helps set this framework and set these rules for design and control. And I think that just in general, copying morphology from a biological system is not enough to get the results that you want in a robot. And instead, you have to actually work through the common language of physics and math in order to really get your robots to behave the way that you want them to. So since we're sort of getting toward the time, I will thank all of my students in my lab, the Robot Form and Function Lab, who've done this amazing work on jumping robots, and some preliminary support from the NSF and from the Mechanical and Aerospace Department and from my postdoc team. And I hope you enjoyed some very quick biological stories. And if you have questions, I'll be happy to take them.
Okay, thank you, Ryan, for the very interesting talk. And so I learned a lot from this interesting creatures behave so interesting. So with that, I think we can start our question and answer session. So if there is any question from the audience, please feel free to unmute yourself and ask your question here. Oh, maybe I can start with two questions. So first of all, so it seems for your robot like a design, you consider the latches, you consider the structure. So how about the material? So have you consider to use different material for your the leg of your robots to improve the behavior, or you think the material cannot behave influence the system much more than the structure and the design of the latches?
Yeah, so I love that question. So I didn't have time to go into it, but one of the things that we can do is even just like a more simple spring, having a material that's responsive to any sort of stimuli or environment. So let's say it's responsive to pH or heat or light. We could then change the spring properties on the fly during recoil, which allows us to even have this additional knob of control in our systems. So, light is relatively fast, and liquid crystal elastomers are also relatively fast. So as long as we are getting into the transient dynamics of the smart material, we could do some really novel control methodologies in spring recoil that wouldn't really be available to us outside of that. And then the other thing is a lot of these biological systems actually store energy in more than one place. So one of the things that we discovered with the snapping shrimp is not only does it store energy in pulling the apodeme, but it also deforms its whole claw shape. So you have this competing, or not exactly competing, but a complementary energy distribution through pulling a rubber band and deforming a shell. And so being able to tailor the material in both of those and tailor the geometry and mechanics in both of those would allow for like a really, really cool design envelope in these systems.
Yeah, then for that to simulate like a different like energy storing system, maybe you can introduce more than one spring, like one spring, when one spring release the energy, then the other can collect the energy back, and then you can do that.
Yeah, I would love that. I will say there was a point during my postdoc where we were trying to do some DIC of ant heads, and it's really, really hard. But ants do store energy in their head, and they use the two recoil of the shell and their apodeme to power their movement. And I did some simulation work where, depending on how we split the energy, we can actually get some of that captured recoil energy. And so we could do something where we have, you know, a mechanically autonomous system, which would be incredible.
Yeah. And my second question, sorry. So my second question, in fact, is about the potential application. So we can see this kind of interesting like robotics design inspired from nature. But in reality, what might be the like a great potential application for this micro robots?
Yeah. So one thing that I always think it would be really interesting is if we have a bunch of jumping robots that can each carry a little sensor node, and whether they jump like very far, very, very fast, and we just kind of dump them on a terrain that we don't really know the terrain, and they all just take off like popcorn in a random way. We can then have them distribute themselves stochastically, and then we can make a mesh network in order to map any sort of area. And I think that this would be actually really cool for exploration of, you know, the moon or other terrestrial planets, especially if we don't really care about recovering a bunch of, you know, small, cheap in a good way, not cheap in a bad way, robots.
Yeah. Yeah, that sounds interesting. Okay. So is there any other question from the audience?
Yeah, Joey, I have two questions.
Yeah, sure. Go ahead.
Yeah, thanks, Ryan. Very interesting talk. I have two questions. One question is about the energy density. You mentioned we can install the energy using the spring so that we can increase the energy density, but actually we can increase the acceleration, not the velocity, because you need to do the integral and of the acceleration over time. Mm-hmm. This is an interesting thing. I'm thinking because this is depend on you use a single spring, right? I'm not sure if there's for biology system, maybe it's very hard. You have multiple spring, but for engineer purpose, you can easily to incorporate 2 or 3 spring, do some rename type of movement. This means you can increase. You first use one spring to accelerate the motion, and at some point you will launch the second, and then you can do. I'm not sure if this is something possible to.
That's great, because, you know, we could do these architectured materials and these meta materials that have these unintuitive scaling properties, which could allow us to, you know, quote unquote, break physics in ways that are even more interesting. Metamaterials and those sort of mechanics isn't really my area of expertise. So, you know, from me, you get the lump spring element model, but this is always a great opportunity for collaboration on how do we design mechanics and how do we design these elements of our mechanical systems to behave in these non-intuitive ways.
Yeah. So my second question is about the energy efficiency. I know that for nature, the biology system usually have very high energy efficiency. So when you design the similar motion using the motor or you engineer the system, how much the ratio compare the energy efficiency to rough?
So I guess in these systems, because the spring is actually what's dictating the energy efficiency, we can kind of black box it and say that we get the energy we'll get from our actuator into our spring. And I'm sure that that is pretty terrible, as most engineered systems tend to be. Polymers are pretty good at being pretty resilient. Obviously, the most common resilient polymer in biology is resilin, which is like 99% resilient. But even some polyurethanes have resiliency that does match that. So the energy efficiency and the energy transfer can still be pretty good in these spring actuated systems.
Okay, thank you.
Yeah, thank you very much for that follow-up discussions. I'm not sure if there is any question from the audience. So if not, I think maybe we can stop our today's seminar here. And we also would like to thanks Ryan again for the very interesting talk. And we look forward to the potential collaborations in the future. So
yeah. Well, thank you for having me. And I hope that I have inspired us all to think about mechanics in a very different way.
definitely.